Bismillahirrahmanirrahim. I'm Dr. Farah Harun. Now you are in fourth year. I welcome you in fourth year. In seventh semester course, we are having a digital signal processing course with code number IE471. In this course, actually, we will just have both the practical and the theory. And in this practical and theory, we will focus not only on MATLAB based applications, but also we will have a DSP kit on which you can just develop your algorithms. Okay, the book that we will follow is displayed here. That is Introduction to Signal Processing, and the author of this book is Sophilus J. Orphanidis. Okay, in this book, we will see, as we have discussed in the previous lecture about the course outline, the first thing we will focus is over sampling and reconstruction, and that would be the chapter number one. In this sampling and reconstruction, why we are doing in case of DSP is necessary because sampling and is prerequisite before any signal processing application. And naturally, if you are having an analog signal being processed digitally, it means you need to reconstruct it back. So basically, sampling and reconstruction are the important sections in case of digital signal processing, and they are crucial. And the sampling is actually pre-processing, you can call it like that, and reconstruction would be post processing. That after processing your signal digitally, the signal would need to be reconstructed back. That's why this reconstruction would be there. So in this case, we will follow these items and sections and subsections that are listed here. Now, let's start from chapter 1 here. And I have highlighted the important uh, points in this, and you need to focus them. So first of all, as an introduction, we will start from here. Just see this block diagram, as I have told you that the digital signal processor is in between, but however, the input of this digital signal processor is your sampler and quantizer. It means the analog signal is that needs to be first digitized before being processed digitally. And in this case, when the analog signal is digitized, it means it needs to be sampled and it needs to be quantized. Later, you can call it like that, that you need an AD converter before preparing your analog signal to be processed digitally. Then comes the main important section, that is digital signal processor, in which the main algorithms are being run. However, the output of this digital signal processor is also digital, and that's why you need an analog reconstructor at the output to reconstruct your processed analog output. Okay, because now the analog input is there, analog output is there, but in between you have signal processes, and that is being done through any digital device. Okay, so basically, digital signal processor can be programmed to perform a variety of applications. You may just implement a filter over it. You may have many other applications. For example, if you are having an audio signal, you can improve its quality. If you're having a video signal, you can change its contrast. So there are several and many applications we are just encountering in our daily life. And one thing more, although there are dedicated DSP signal processors for doing this job, but however, the course is focused that you can even develop this signal processing algorithms either on your microcomputer, either on your microcontroller, or any digital device. So basically, you will need certain hardware to process it, and it would depend that how the signal is being processed. Okay, then you are having some basic concepts of sampling and quantization that we have already done, and we will just come to that section. It is now section number 1.3. Here you are having your sampling theorem. Okay, basically the sampling theorem we have done previously also, but you will see some new concepts that would be added to your previous knowledge. Here what we are assuming, x of t x of t is a continuous signal, and this x of t is periodically measured every t seconds. It means this x of t is a continuous signal and it is being sampled out after every t seconds. That means t is actually your sampling interval, okay, or your sampling time. And this sampling interval t is there, and when you are having a continuous time t and you are just converting into a discrete time, it means t would be replaced by nt. N would be an integer that would arise from 0 till so on, and where t would be your sampling interval. Okay, so here in this sampling interval, it means first, for example, n is 0, it means you are collecting your first sample. When your n is 1, it means you are collecting your second sample, and likewise. However, in the effect of sampling in time domain is to convert a continuous time signal into a discrete time signal, but its effect in frequency domain would be the addition of high frequency components, and these high frequency components would be added in the original spectrum of your signal. It means the effect of sampling on what is the effect of sampling on the original frequency spectrum. It means in the original frequency spectrum, lot of spurious high frequency components would be added, and your original frequency spectrum would be replicated after every interval of sampling frequency or sampling rate. And the second important thing is in this section, we will just learn that how we should select the sampling interval t. So here, just see, the original signal is periodically replicated over the entire frequency axis. This is the effect of sampling in frequency domain, and this sampling just leads to replication of a spectrum of the original signal after every fs, that is after every sampling rate. Okay. For example, now you are having a sinusoid that is being expressed as xt e to power j 2 pi ft. It means it is a complex signal. It would have sine and cosine terms both. And here, what you observe that if you are having this type of signal that is only having one frequency signal f, it means spectrum would be a single line spectrum, and that is appearing on the next page in figure 1.3.2. Okay, so here you can see a sampler can be modeled as a switch. Okay, an ideal sampler can be modeled as a switch. For example, analog signal is appearing at its one input, and whenever the switch is closed, whatever is appearing at x of t would appear at x and t. And when the switch is opened, it means the signal at the output would be zero. It means the making of the switch is for just an instant, and the closing of the switch is for very comparatively larger time, so that you will have this type of signal at the output. If this x of t is a continuous time signal, now you are having this signal that is being sampled out. It means the switch has been closed after every sampling interval, that is t. You are having your first sample at 0 when n is 0. When you are having your n1, you are having this sample. When n is 2, you are having this sample, and so on. So it means this is the effect of an ideal sampler. What the job of ideal sampler is, it converts the continuous time signal into discrete time signal, and then becomes over its spectrum. Here what you observe, that if you are having a single frequency sine wave or single wave frequency and signal, its frequency would be just having a line spectrum at f. Okay, this single line spectrum, single frequency that is appearing as a line spectrum at f, once when the signal has been sampled out, it means there would be a spectrum replication as shown below. Here what you observe, that the original spectrum at its own place, but this spectrum is being replicated after every fs. It means the second time it will appear at f plus fs, then f plus 2 fs, f plus 3 fs, and so on. And similarly on the left hand side also. So it means here what you have learned, we have learned that the sampling in time domain leads to conversion of continuous time signal into discrete time signal. Okay, but the amplitude is still continuous, only the time has been digitized. Okay, but the effect of frequency is in terms of the replication of the spectrum, that you see that here is f, then again this spectrum is being replicated after every fs on both sides. It means your n will take plus minus both values. Okay, one more important observation is that if any of these frequencies, any of these replicated frequencies, if can be generalized and specified as f plus mfs. Okay, it means the set of these frequencies can be expressed as f dash would be f plus mfs, and give m as, treat m as an integer, that is first it would be 0 and then plus minus 1 plus minus 2 and so on. It means you are having a complete set of frequencies, infinite set of frequencies that are being appeared as, and in this what we are doing, we are just adding and subtracting the fs integral values of fs. Here you will get a complete set of frequencies. Important observation is that if, for example, any of these frequencies is sampled out at rate of fs, the sampled signal would be indistinguishable. Okay, what I'm saying, any one of them has the same periodic replication when sampled. It means if any of these replicated frequencies is sampled out, then the sampled version of these signals would be indistinguishable. You would not be able to realize that either I have sampled out f plus fs, or I have sampled out f, or I have sampled out f minus 2fs. But keep in mind, keeping the sampling frequency same. If you just keep the sampling frequency same and then sample out any of these frequencies, the sampled signals would be indistinguishable, and this is called as aliasing. Okay, and how it can be avoided, that may be done, and then we will do in the next section. One more thing here, for example, if you are having this type of two signals here, signal 1 is there and signal 2 is there, and both are being sampled, what you observe, there is no variation in signal 2. It's very slow, it is very slowly varying signal 2, whereas signal 1 is comparatively fast changing quickly, and it is just a sort of sinusoidal function. So here what you observe, that in case of signal 1, the sampling is quite good, but in case of signal 2, it is being oversampled because the changes are producing very slowly, and that's why, and you are collecting more samples of it. So it means here signal 2 is oversampled. So here, how do we decide that at which frequency we need to sample out any signal, is given by the sampling theorem. And this sampling theorem is give you the thing that you can only get the accurate representation of accurate signal x of t by its sample x and t when two conditions are met. Number one, the signal xt must be band limited. It means it should be band limited. Band should get zero after any frequency, maximum frequency value. That is, the frequency spectrum must be limited to contain frequencies up to certain maximum, that is f maximum, and beyond f maximum the spectrum should not exist. And second is what? The sampling rate fs, that at which frequency you will sample out signal, should be at minimum double your maximum frequency. It means the thing is what? First you have to identify the maximum frequency component in your signal, and then you need to define the sampling rate. Always the sampling rate should be less than equals to 2f maximum. This is theoretical expression, but in case of practical, you need to at least keep it comparatively much higher as compared to double. Okay, and if the sampling frequency is written as twice of f maximum, that is the maximum frequency component present in the signal, respectively the sampling interval would be inverse of your sampling frequency, and in this sampling frequency you can put 2f maximum again. So it means your sampling interval should be less than or equals to 1 over 2f maximum. Okay. Here you see a band limited signal. What I have told you, that a band limited signal would be a signal whose frequency spectrum means its Fourier transform should get zero after certain maximum frequency. So here you observe your x of t is a time domain signal and its spectrum or Fourier transform is mentioned as xf. So here you observe that xf only exists between minus f maximum and f maximum. Beyond f maximum and below f minus f maximum, the x of f is zero. That means this would be called as a band limited signal, because here the spectrum does not exist for infinite values of f. Spectrum goes to zero, it means its value is zero beyond certain f maximum value. So here this fs equals to f maximum is called as a minimum sampling rate, that is also called as Nyquist rate. Okay. Later we define another term that is called as Nyquist interval, and this Nyquist interval is what? Nyquist interval would be a band of frequency, a range of frequencies starting from half of the sampling frequency till half minus side till fs by 2. It means this Nyquist interval would be defined from minus fs by 2 comma fs by 2. It means half of the sampling rate would define the Nyquist interval. Okay, there is, you will see that there is a very great significance of this Nyquist interval in upcoming discussion. However, remember that if fs is your sampling frequency, for example, fs is, let's suppose, 10 kilohertz, then your sampling interval would be what? It would be minus 5k to 5k. It means minus fs by 2 till fs by 2. The Nyquist frequency fs by 2 also define the cutoff frequencies of the low pass analog pre-filters and post filters. So here what you observe, that you are having an Nyquist interval from minus fs by 2 till fs by 2. Why I have told you that it is very important? Because the cutoff frequencies of your pre-filter and post-filters. Pre-filter is one which is connected before DSP processor, and post-filter would be one that is connected after DSP processor. Both are having their cutoff frequencies defined by fs by 2, and it means your this pre-filter, that is, if it is cutoff frequency is fs by 2, it means it will not allow any frequency greater than f maximum to enter into your DSP processor, and this f maximum would vary based on your application. That, for example, here in this table, you have listed the F maximum and their respective sampling frequency. If you are having an audio signal, it means your maximum frequency would be 20 kilohertz, and then that's why its respective sampling frequency would be Fs. Similarly, for video, it would be 4 megahertz, and then respectively double of it would be 8 megahertz, and so on. So several applications are specified with their F maximum and their respective sampling frequency. Now we come to the anti-aliasing pre-filter. Anti-aliasing pre-filter is the one that is, you call it as pre-filter. Here you can observe, it means this filter would avoid aliasing. Anti-aliasing means what? This filter would avoid aliasing. That will appear if this pre-filter is not there, and if you try to directly sample out your input signal without passing it through analog low pass filter, then there would be the chance of aliasing. But if you want to avoid aliasing, then what you have to do, you have to put an analog low pass filter in front of your sampler and quantizer. So here what you observe in this figure, that is, this is your analog low pass filter. Its cutoff frequency is defined as fs by 2. It means you're based on your sampling frequency, half of the sampling frequency would be defined as its cutoff frequency, and that will also be your f maximum that would be entering into this system. So here, this is fs by 2. From this picture, what you observe that this gray was the original spectrum or input spectrum of the signal xn, but once it has been band limited, it means the corner edges would be removed out, and you are having your signal truncated between minus fs by 2 to fs by 2. The signal is now band limited. Then this band limited signal is fed into a sampler and quantizer. In the sampler and quantizer, what you see that you are having the replication of this spectrum. It means the input spectrum, that is this pre-filtered spectrum, would be replicated after every fs. In previous example, we have observed that your input signal was just a single sinusoidal function, and that's why you are having a single line spectrum that was replicated after every fs. But here in this case or in this picture, we have assumed that your input spectrum is a continuous spectrum. It is having a band of frequencies in it, and that's why when you are having a band of frequencies in your input spectrum, the whole band would be replicated. So it means first it has been filtered out, now the edges have been removed, the signal is being limited between minus fs by 2 to fs by 2, and then this spectrum that is appearing at the input of the sampler and quantizer would be replicated for this discrete time signal, that is x and t. It means x and t is in digital time domain, whereas this spectrum is shown in frequency domain. Okay, the output in this case in free time domain would be a set of impulses or a set of sampled signal. Okay, so don't be confused. This picture is not of x and t. X and t is a discrete time signal, sampled signal, and this discrete time signal is having this spectrum in frequency domain. Okay. Now, we will do certain examples, and based on these examples, you will have a better idea that how this pre-filter would work out. Okay, just stop it here. Then, inshallah, we will just have problems over this.